We traditionally define weather by the sky. We look for the buildup of clouds and the movement of wind driven by solar radiation across the open landscape. Deep geology suggests something much more inert. We imagine caves as vaults of stagnant air, locked in stone and completely detached from the systems of the surface. Yet, deep within certain cave systems, the environment is anything but still. Explorers can be hit by a forceful wind emerging directly from darkness. This isn't the result of a surface storm or a hidden ventilation shaft. There are no machines or fans powering this airflow. The cave itself is circulating air, operating like a giant natural lung. Understanding how a hole in the ground generates its own wind requires looking at the rock as a thermodynamic engine. These systems represent a self-contained microclimate, functioning independently of the broader regional weather. Rock acts as a dense thermal buffer. Surface temperatures spike and plummet, but miles underground, temperatures remain constant. This creates a thermal clash. The chaotic surface heat meets the stable deep cave, causing an immediate physical imbalance. Physics dictates that these two environments must attempt to reach an equilibrium. Because warm air is less dense, it expands and rises, while cooler, heavier air sinks toward the lowest possible point. This vertical movement creates sharp pressure gradients within the rock chambers, with high and low pressure zones shifting as the air seeks a path out. This pressure is the drive behind the wind, turning a network of tunnels into a functional thermodynamic circuit. Geologists call this the chimney effect. Powered by an expansive network of hidden passages, tiny surface fissures act as intake valves. They pull outside air, funneling and concentrating the draft into a powerful gale at the main opening. This wind also drives a subterranean water cycle. Groundwater constantly leaches through the porous rock, seeping into the air-filled chambers. As the dry wind rushes over these damp surfaces, the water evaporates, fully saturating the cave's atmosphere with moisture. When this moisture-laden air hits a colder section of the cave wall, it condenses instantly. Under the right conditions, this creates a spontaneous subterranean fog and thick mist, effectively raining directly inside the cavern. This process is entirely dynamic, shifting its behavior based on the planet's seasonal tilt. In winter, the cave remains warmer than the frozen surface. Warm air rises and pours out of the entrance, meaning the cave is effectively exhaling. By summer, the cycle reverses. The cave air is now cooler and heavier than the surface heat. It sinks outward through the lower exits, while drawing hot surface air in through the upper cracks to begin a long inhale. This rhythm ensures the cave remains in constant, breathing synchronization with the world above. This phenomenon suggests that caves are not isolated geological features, but active participants in the global atmosphere. The surface and the deep underground exist in a state of continuous exchange. They swap heat, moisture, and gases in a cycle that supports life far beyond the reach of the sun. It proves that the atmosphere does not stop at the surface of the soil. It extends miles into the Earth's crust. These specific weather conditions support unique ecosystems, including bioluminescent colonies that depend on the cave's humidity loop to survive in total darkness. Exploring these depths reveals that the planet is not just a solid ball of rock, but a living, breathing system where every layer is physically tied to the sky.